Hi dear students, this is from the fourth module of subject EST 100 Engineering Mechanics. In this presentation, I would like to discuss about work energy equation and impulse momentum equation. These are the two important equations used in the field of dynamics. So first we will discuss work energy equation. So work, it is the product of force and displacement. Work is defined as the product of force and displacement. The unit of force is, we know that it is Newton, and the unit of displacement is meter. So the unit of work will be Newton meter, and it's also known as simply joule. So 1 Newton meter equal to 1 joule. So here it is the representation of the work done. So force P is acting on a particular body, and due to that force, along the direction of the force, the body is moving a particular distance x. Now P is the force acting on the body, and S is the distance traveled by the body in the direction of the force. Then by the definition of work, work done is defined as the product of force into displacement, that is P into S. Remember, we will be considering the force along the direction of the motion only. So that we will see in the next slide. That is, if the force is inclined at a particular angle theta degree with the direction of the motion as shown in figure. See here, the force P is inclined at an angle theta to the directional motion of the actually the directional motion of the body is along the horizontal, but P is inclined theta degree to horizontal. So P is actually acting in a particular inclination. As I told earlier, while calculating the work, we will be using the force along the direction of the motion only. So we have to resolve that force along the direction of the motion or horizontal direction. That is, the component of P here along the horizontal direction is P cos theta. Therefore, work done will be P cos theta into S. So if at all force is inclined at a particular angle, then we want to find out the work along a particular direction, then resolve that force along the directional motion of the body. Now we will define what is energy. Energy is the capacity to do work. It is a sum of potential energy and kinetic energy. Some other forms of energy are also there, but we will be considering, in the field of mechanics, we will be usually considering potential energy and kinetic energy only. Unit is same as work, that is Newton meter. The kinetic energy of mass m moving with velocity v is given as half mv square. I think all will be knowing. And potential energy of a body of weight w held at a particular height h is w into h or mgh. That is the equation to calculate kinetic energy and potential energy. Kinetic energy equal to half mv square and potential energy equal to mgh. Now we will move on to our topic, that is work energy principle. It states that work done by a system of force acting on a body during the displacement is equal to the change in kinetic energy of the body during the same displacement. So due to the effect of some forces or due to the cumulative effect of a system of forces, assume that the body is moving along a particular direction. If it happens, then as per the work energy principle, it says that the work done by the system of force will be equal to the change in kinetic energy. So we can equate work done to the change in kinetic energy of the system. Okay, and now we will move on to the proof. Consider a body of mass m moving with a velocity u. Initial velocity of the body is u. Let s be the displacement of the body and v is the final velocity. Now F is the resultant force acting on the body. Now from Newton's law we have F is equal to ma, where a is the acceleration of the body. And we know from the definition, acceleration is nothing but rate of change of velocity. So a is equal to dv by dt. This can be rewritten as dv by ds into ds by dt, since ds and ds will cancel, so no change in the value. So dv by dt equal to dv by ds into ds by dt. But we know that ds by dt is nothing but rate of change of displacement, or displacement by time, that is velocity. So this can be written as v into dv by ds. So acceleration is written as v into dv by ds. From Newton's law we have F is equal to ma. Therefore F is equal to m into, instead of a, I am writing that v into dv by ds. So F is equal to m into v dv by ds. So I am taking that ds to the left side. So F ds equal to m into v dv. Now integrating on both sides, integral 0 to s, F ds equal to m into integral u to v dv. Velocity changes from initial velocity u to final velocity v, and displacement is from initial 0 to final s. So F is constant, can be taken outside. So first term integrating ds will become s, and the limits are 0 to s. And the second term here v dv, integral of v dv is v square by 2, and the limits are u and v. On substituting, F into s minus 0 is equal to m into v square by 2 limit uv. So initially substituting v higher limit v, and secondly substituting the lower limit u, the equation takes the form f into s. Here it is s minus 0, so it becomes s. Here it is s minus 0, so it becomes s, and m into first limit is v, so v square by 2, and second limit is u, so u square by 2 minus u square by 2. So f into s equal to half into, if m is taken inside, so half into m into v square minus half into m into u square. As I already told, half mv square is the kinetic energy, so this is the final kinetic energy and this one is the initial kinetic energy. So total it is change in kinetic energy. That is what the work energy principle says. This left side it is f into s, force into displacement, that is nothing but work done. So work done equal to change in kinetic energy. So this can be useful to solve problems in the field of mechanics. So we will see a sample problem. A block weighing 2500 Newton rests on a level horizontal plane for which coefficient of friction is 0.20. Coefficient of friction is given and weight of the body is given as 2500 Newton is shown here. W is the weight and friction coefficient of friction is 0.02. The block is pulled by a force of 1000 Newton acting at an angle 30 degree to the horizontal. You can see that force shown here. The force P is acting at an angle 30 degree. It is pulled, so it is force is outward. So 30 degree to the horizontal. Find the velocity of the block after it moves 30 meter starting from rest. So it states that initially the body is in rest. We want to find out the velocity after it has moved 30 meters. So distance is 30 meters. S is equal to 30 meter and initially U is equal to 0. If the force of 1000 Newton is then removed, so after moving 30 meter the force P is removed. So since it is initially it was in rest, but due to that force it has started moving, it has moved a particular distance 30 meters, so it has acquired a particular velocity. After that the force is removed, means due to the momentum it will be moving further. So how much further will it move? That is the second part. Use the work energy method. It is specified that use the work energy method. Otherwise we can solve this problem using the other conventional methods also. So that's why in the question it is given use work energy method. If it is not specified, you can do it by any method. It's no problem. So moving into the solution part. Free body diagram of the block and the two cases are shown in figure. When pull P is acting, initially the case one is force P is acting. So here you can see weight is acting downward and normal reaction will be upward. So N will be equal to, if you write the sigma Fy equal to 0, equilibrium of this state, then you will get W minus P, W is downward, W equal to, W is downward, so I am taking downward as positive, so W minus P sin 30 minus N is equal to 0. From that you can find out the value of N, that is what is written here. N is equal to W minus P sin 30. So you will get the value of N is equal to 2000 Newton. Once you got the normal reaction, you can find the frictional force, frictional resistive force F is equal to mu N, or you can this is actually R. Instead of R, instead of N you can replace it by R. That is what we have studied in the earlier portion. So F is equal to mu R or mu N. Substituting, you will get F is equal to 400 Newton. So frictional force is 400 Newton and it will be acting always against the motion of the body. Since P is acting in this direction, so the motion will be along, frictional force will be opposite to that. That is what is shown in here in this free body diagram. So now our aim is initial velocity is given as 0, U is equal to final velocity. We are assuming that final velocity is V, displacement S is equal to 30 meter. Now applying work energy equation, what work energy equation says is work done equal to force into displacement. So as I told, we have to calculate the net force along the direction of the body. So here the body is moving towards the right, horizontally towards the right. So we want to find the net force acting in this direction, that means sigma Fx direction. So along the x direction, P cos theta is towards the direction of the motion, P cos 30, not theta, P cos 30, but F is opposite, so it has to be taken as minus. So W and N are acting vertical direction, so it won't have any component along the horizontal direction. So here you can write as P cos 30 minus F into this term is net force into S will give it work. So work equal to the P cos 30 minus F into S is the work, equal to change in kinetic energy. Changing kinetic energy half m V square minus U square. Actually instead of m 1 by 2 is here. Instead of m, I am writing as w by g. M is equal to weight by g, or w equal to m into g. From that you will get m equal to w by g. So w by 2 into g, half m v square minus u square. So only unknown term is v square. So from this equation you will get v is equal to 10.4745 meter per second. Now this is the v before the force is removed. So once the force, second part is force p is getting removed, that means at that time the body is having velocity v. So initial velocity for the second case, initial velocity is this one, 10.47, and final velocity, finally the body is going to stop. So final velocity is 0. Now applying work energy equation for the motion in the horizontal direction, here there is no p. Second case, this is the free body diagram. Here there is no p is acting, only force acting will be resistive force against the motion. Here also the body is moving in this direction only, but force is in the opposite direction. So force into displacement, F into S. Here you can see a minus F, since actually F is acting opposite to the direction of motion, that's why negative. Minus F into S, that is work. As in the earlier case, from work energy principle, it is m into half m v square, v square minus u square. So w by 2g v square minus u square. Here v is 10.47, sorry, u is 10.4745 and v is 0. So substituting here, left side also one minus is there, right side also you will get one minus. So minus and minus will get cancelled. So s is equal to 27.96 meter. So the body will stop after traveling a distance of 27.96 meter. Now we will see impulse momentum equation. So when a large force acts over a short period of time, that force is called impulse